computer engineering at UIUC, and Bose received his PhD and master degree both from Caltech, and he was also a postdoctoral fellow at Cornell University. He's the recipient of 2021 NSF CAREER Award, and his research interests are about facilitating the integration of renewable and distributed energy resources into the grid by leveraging tools from control, optimization, and game theory. So Bose.
Thank you, Rasul. I'm Bose, as Rasul mentioned, and my work is in the area of power systems and electricity markets. So we've heard a lot of talks on the theoretical foundations of data learning and markets. And so when Rasul asked me to, or invited me to give this talk, I thought, well, let me talk about the role of data learning and, of course, electricity markets that I study in my field of expertise. Okay, so let me begin this talk by sort of outlining a few trends that are there today in the power system that are inviting new research questions and directions that are amenable to sort of mathematical inquiry that most of us are interested in. Okay, so what are some of the trends? So if you look at sort of the generation portfolio of the United States, it's really, really changing fast. So think about large centralized power plants, mostly fossil fuel based, where coal was the main producer. Today, even in the fossil fuel world, it's being replaced by natural gas, and a lot more of the capacity additions are from solar and wind, right? In fact, there was a day earlier in this year where 98% of the demand in California was met by renewable resources. So it's really no longer on the sidelines. They are becoming the main actors, right? That's happening at the transmission level, which is the backbone network of the power system. What about the grid edge, where you're looking at people like you and me, with rooftop solar, our distributed generation? I've looked at data sets where people are net producers of electricity. People's homes are net producers of electricity for a part of the day, right? And you have flexible resources where you can have intelligent thermostats that are controllable. So the distributed energy resources that are there at the grid edge are providing a flexibility that never existed in the power system, right? The consumers have grown up; they're becoming prosumers, right? So, and now the FERC order that came out last year on the 2222, it actually now paves the path for DERs, or distributed energy resources, to be active participants of the energy economy through aggregation. Makes sense? And these kinds of resources mostly are connected to the grid through inverters. And these inverter-based resources, they pose different dynamics. They sort of, and their dynamics are somewhat different and change the kind of stability considerations that we must look for. So some of it will show up in the talk, in the later part of the talk. Now, on the demand side, if you look at it, if you look at these projections of demand growth from the ISOs, you'll see that people project the demand will go up, and then the next year they produce, again, the same graph, shifted by 1 year, shifted by 1 year. I've seen these graphs. Demand has never really gone up because we are doing more with electricity, but we are also becoming more and more efficient, right? But that is about to change. If electric vehicles hit the market, this is no longer going to be the case. A particular electric vehicle can look like basically a house from the perspective of a grid, right? So think about how much that would increase the demand. And their demands would be spatio-temporal, because they can drive from one place to the other. And where they demand, when they demand, is going to depend on human behavior. So a lot is going to change on the demand side. And this is unfortunate. The climate change-induced disruptions that have happened, one very recently in Florida, right? There have been ones that have been in Texas. So this is fairly recent on our minds. So a lot more uncertainty in the sort of the grid that we are having to endure, right? Some of it is human-induced. We are trying to get towards more and more renewables, solar and wind being more and more stochastic and so on, but this is happening to us, the uncertainty is given to us, we have to optimize against it. So far, so good? All right. So these are sort of the trends. Now, what do I do with this? The topic of this talk is role of data. So what I thought about is let me pick a few problems where I'll sort of try to understand the role of data. And what we have done, pose some questions that I don't know how to answer. Hopefully, some of you will answer. And I will get to collaborate with some of you. And some of the things that we are actively working on. Okay? So if you think about power system, you have to look at daily operations, right? I mean, 5 minutes ago, a market has just cleared in the real-time markets, and based on which the demand and supply is affecting right now. This projector is on. I'm part of the demand, right? We are all part of the demand. And so in daily operations, I would like to see what's the role of data in wholesale market design, which is the wholesale markets that are running at the system operators level. People are thinking about the retail side. The DERs are coming up. So people are thinking about what is the kind of mechanism that can be used to harness the flexibility of these resources. So some ideas for retail market design. And when you think about power system is an infrastructure. It's an infrastructure where investments have to be made with long-term projections, right? And so long-term planning will talk about a little bit of hosting capacity analysis, where the question that I would pose is how much solar is too much for the distribution grid? And finally, look at some questions on transient stability analysis, which is sort of a core question in power engineering we are having to open up and revisit again because of these inverter-based resources. Now, in each of these, the role of data will be slightly different. The one that are in 1 and 1 here, the data is to process uncertain futures. So essentially, you will have to somehow process possible futures with their probabilities and so on, and try to optimize against it. So that's in sort of the role of data in the ones that are marked as 1. The second part is retail market design. I'll talk about the role of data is in learning user preferences, which we have seen a lot in this particular workshop. And in the transient stability analysis, the reason that we need data is because of incompatible models, and why that is the case and what we can do in certain ways how to tackle them for this particular problem. By no means is this the only problem that power system cares about, but this is one that we've been thinking about. So far, so good? All right. Part of this, I'll talk about where it's our work that we've done in the past couple of years, and some of it will be new research directions, and some of it will be what we are actively working on. And now, I truly believe this. If you're looking for interesting problems with practical applications, I find the electric power grid is a modelless paradise. My training was from optimization control game theory, but I find because it's a networked and hierarchical cyber physical system featuring multiple interacting agents with strategic incentives. So think about basically everything that we talked about. There is some role of that math in power system. Make sense? So with that introduction, let me jump into processing uncertain futures with data. And the first part of that, so I'll divide this into two. As I said, in my 1, there are 2 parts, wholesale market design and hosting capacity analysis. So let me do the first part, which is wholesale market design. By specifically what I'm interested in is looking at risk-sensitive wholesale electricity market design using data. Okay? So when I have to process uncertain futures, one classic way of looking at or processing that uncertainty is through a risk measure. You can open up a book on stochastic optimization, and I mean, there's a very long and rich literature on risk measures, and you can include one of them and try to solve a risk-sensitive, some electricity market optimization problem. Great. So what I've been looking at and I've been interested in is processing risks with a conditional value at risk measure. The idea is very simple. Think about a loss which has some PDF, right? If I give you this CVaR of this loss with a parameter alpha, let's say the alpha is 0.95, I'm looking at 1 minus 0.95, that is 0.05, which is 5%. I'll look at the 5% worst case tail of this distribution and take its expectation. That's conditional value at risk. Makes sense? And now that admits a particular variational characterization due to Rockefeller and Uryasev. And it turns out you can generalize this. This interpretation is good for random variables with continuous distributions or smooth distributions, or PDFs. But you can generalize this to arbitrary distributions through this formula. So far, so good. So this is conditional value at risk. Why do I want to think about this? This sort of has few properties that I care about. If you process uncertainty through its expectation, you are exposing yourself to multiple instances that can be really bad for you. If you're processing it through the worst case, you're sort of being too conservative. So this measure with this particular factor that is tunable, I have a flexibility of choosing my risk preference. Make sense? And the beauty of this particular variational characterization is that it is really amenable to analysis in many ways. First, it retains convexity. If you have a deterministic optimization program for which you're writing the risk-sensitive one, and under fairly mild conditions, this retains the convexity of that optimization program. If the deterministic program was convex, this would be convex, which means I can design efficient algorithms, sometimes even just leverage tools that are there already, and I can just throw a solver at it, right? And then, when you think about electricity markets, you have to think about pricing. No electricity market design is complete without pricing. And pricing is typically based upon duality theory. Now, convex programming is duality theory. I can just borrow and analyze prices. Make sense? So this is sort of my way to deal with the uncertain futures with data, but with conditional value at risk as my way to process it. And as we will see in data, yes?
So how are you going to use this quantity?
Conditional value at risk? Oh, I'll go to.
You talk about that it remains convex.
Yes. I'll get to it just in a second. So the electricity markets operate under the simplest way to perhaps, and this is embarrassingly simple, way to sort of present this. You solve an optimization problem which looks as such. You're trying to minimize procurement costs of whatever controllable resources you have. They have their own set of constraints. And you can think about G as the generation and D as the demand. And whatever this is the net injection into the power grid that has to satisfy a bunch of constraints of the network. So these are resource constraints. These are network constraints. Make sense? And this deterministic problem suitably done with power system models or power network models with a simplified linear program version of that is used today extensively. The question is, how do I process uncertainty? What is uncertain here? Now, two kinds of uncertainties. Think about a line going down or a generator going down. I call this discrete uncertainty. Their support set is discrete. So these are basically a collection of what-if component failure scenarios that you have to guard against, right? We've done some work in that, but today I'll only discuss the one that is on continuous uncertainty. And so here, what we are looking for is think about the demand as net demand rather than just demand minus renewables, and that is a stochastic quantity. We have to look at it from a forward market perspective. Why? Think about the following statement. If I had infinite ramping capabilities in my generators, I don't need to solve a stochastic optimization problem and plan for it. I can just ride the wave. Unfortunately, I don't have that ability in a power system. Certain generators take 3 days to turn on. Certain generators have ramping capabilities that are limited. So that's why I need forward planning. Make sense? And so that forward planning, I want to do in a risk-sensitive way. How? And so for this particular space, if I'm going to assume that the power flow model is linearized so that everything is much more simple, typically what is used in electricity market context. If you want to look at it in the context of with the non-convexity, I did most of my PhD trying to think about algorithm design there and even some pricing. Recently, some work with my student Mariola and Anna, who's in the audience, a recent work that we had done. But long story short, what I would look at right now and present some results on looking at a risk-sensitive market design problem here with continuous uncertainty that accounts for large forecast errors in wind and solar output. Yes? This is day-ahead market. I would like to do day-ahead market. Okay, a risk-sensitive day-ahead market design. Okay. Okay. So if I were to take my demand as being is net demand, where it is demand minus the renewable output omega, which is random, and then my generation should respond to it, right? And so whatever the forecast error is, let me say that my generation would be an affine feedback of that particular forecast error. So then a CVaR penalized, CVaR constrained formulation of the market clearing might look as such, where you have a minimizing sort of conditional value at risk of the cost. Cost now becomes random, right? And then I have an almost sure constraint here, which is the demand and supply balance. I can't play around with it. That you have to. This is physical law. You have to impose always. But what you can allow is a little bit of violation of constraints like line flow limits and so on. But you're penalizing through a conditional value at risk. Why? Because not only do we care about the probability of violation, but what CVaR gives you is automatically a control on the extent of that violation, because I'm penalizing the expected value of it. Make sense? Okay. So this particular problem, if you squint your eyes a little bit and sort of believe me that there is a way to get rid of this due to the nature of the simplicity of this constraint, I can write these problems as an example of a problem of this form. And so I'm going to present some results that we've obtained recently on this particular form of that problem, where it's a CVaR penalized, CVaR constrained optimization problem. Now, these kinds of optimization problems are extremely expressive, right? If I take alpha to 0, this becomes expectation. And if I take alpha to roughly 1, this is the essential supremum, which means the maximum, or I'm solving a robust optimization problem in some sense, right? And similarly, the constraints, you can think about the same. And there's a lot of work that has happened in chance-constrained optimization, Campi, Calafiore, Garati, et cetera. And we were sort of inspired by their work. And chance constraints have a very, very interesting relationship with conditional value at risk. It's not very difficult to think about it. This is a convex inner approximation. A conditional value at risk is a convex inner approximation of chance constraints. Okay? Yes? It's a very good question. Right. So the more recent formulation is slightly different from this, where it mostly makes sense is in the constraint, in my opinion. And the reason is the following. So you're procuring reserves so that you are minimizing the risk of failure of meeting some constraint. Now, constraint violation, for example, line limits, you can exceed for a little bit, because these are typically thermal in nature. So if you heat up a line a little bit for 15 minutes or half an hour or 1 hour, there's a limit of how much you can load it, but you should bring it back. So that's the interpretation. So, but how much you load it, that matters. It's not just the probability of violation, but the extent of the violation. Okay. All right. So the kind of results that we have obtained, I'll sort of quickly summarize this. So first, we started looking at the very simple problem where alpha and the betas are 0, which means that I'm looking at expected value minimization subject to expected constraints. So we looked at a stochastic primal dual algorithm. This is it's our classic algorithm with one twist. For the dual update, I don't use the same sample. I sample it again. So there are 2 samples per primal and then dual update. Make sense? And this is a classic version of it. And then what we essentially could show, I mean, I'll get to the results, once we analyze the performance of this, and then we try to generalize it to the CVaR problem using that variational characterization. Now, the kind of results that we obtained here is that you can get a 1 over an order optimal convergence rate, which is 1 over square root k, with a constant step size. Okay, and I'll come to the sort of the highlights of this analysis. And once you do that, after that, what you do is you can try to optimize. Suppose you give me an epsilon threshold. This is the amount of suboptimality and constraint violation I am ready to accept. Then I will optimize my step size and even my number of iterations based on that epsilon you provide. And you can actually characterize that. Now, once you do that, then I can apply this to the conditional value at risk problem, because once you, again, squint your eyes at the CVaR problem, that variational characterization looks like an expectation that you're trying to minimize. So it's a matter of now figuring out what those constants are and how they scale with the risk parameters. Make sense? Now, a major highlight of whatever we sort of did in this particular analysis, the highlight of our analysis is the following. We sort of end up removing a requirement of bounds on the dual variables. This is sort of a limitation of, or the proofs required it till now, and sort of our proof technique is such that it sort of circumvents that requirement. And we are able to still provide order optimal guarantees. Now, why this is order optimal, by the way, just to, if you look at the particular problem here, we don't assume smoothness, but we assume convexity. For just minimization of a non-smooth but convex optimization problem, you can't do faster than 1 over square root k, Nesterov's famous result. So you can't do better than this, and we match that rate. Okay. And so just one sort of example that I want to show you, I mean, without getting into the details of this, for a very simple problem, as you change alphas and betas, this is the optimized number of iterations that you require to solve this problem. Notice that as you become more and more risk averse, your number of iterations and the number of samples are growing, right? So when you think about modeling your problem and you choose your alpha betas based on your application requirement, this is sort of a computational cost of robustness. It's very similar to what Campi, Calafiore, and Garatti style results in chance constraint optimization looks like. The more risk averse you are, the more samples you need. This is not very surprising if you think about it. I need to look more into details of the tail to be able to guarantee certain things, so which means I need more samples. Make sense? All right. And this is the paper that appeared in JOTA last year on this work. Okay, so I can do some optimization problems. Can I do pricing in my electricity markets world? Now, again, with the same kind of electricity market clearing setup, if you use a few more approximations, these are sort of motivated by a paper by Yuri Vorkin, and then you replace the conditional value at risk with its variational characterizations, and how do you then solve this to get prices? Using that variational characterization, if you replace them and then associate some Lagrange multipliers, you can now define what is a risk-sensitive locational marginal pricing. And the formula looks, if you are familiar with this literature, it looks exactly the same as what the deterministic variant is. However, the constraints here are coming from a stochastic optimization problem. Make sense? And you can show certain things that are sort of what you would expect. Just want to talk about just one point. That is, if you take the wind variance or your stochasticity down to 0, you recover the exact deterministic LMP that we are used to. So this is a generalization of the locational marginal pricing schemes that we are used to that is currently there in electricity markets. This provides a risk-sensitive generalization. Yes?
So in the figures you showed, what was the alphas that you typically choose?
In these ones?
Yeah.
So here it's ranging from everything. It's going from 0 to 1, right? I'm taking all of them and just plotting it.
Alpha going to 1 is very sensitive to risk.
Yes. I mean, actually, if you think about it, alpha reaching 1 means what? You're trying to almost solve a robust optimization with a sample.
Right. So
It necessarily must blow up to infinity.
yeah, that's correct. But I guess what I was wondering is that
How does it vary?
no.
So it looks this way.
Do something like some sort of important sampling technique. What you're estimating is such a small
I agree.
probability.
I agree.
Yeah.
I agree. And I don't have an answer for that. One of the research questions I want to pose has something to do with this. Okay. All right. So can you estimate these things from data? Yes, you can. You can do the sample average approximation for all the expectation. You take empirical means in terms of expectations, and you can solve these, and you get these prices. Are these actually converging somewhere? We are trying to prove that. Yeah. Yes? So whenever you think about wind or solar as, it has a compact support, because the maximum you can produce with the wind is whatever the wind farm's nameplate capacity is, installed capacity is, right? So, yeah. And in fact, if I recall correctly, the analysis for the expectation part did not require it, but the conditional value at risk part required us to bound or assume a compact set, if I recall correctly. Okay. How do you set capital N? It's a very good question. So, I mean, all we currently know is that if you, sample average approximation for a particular risk measure, that's what we are utilizing here, and replacing expectations with empirical means. That's all that there is, right? Now, once you try to calculate the locational marginal prices, these are basically locational marginal prices as a function of n. And as you see, they are sort of starting to show some convergence. Where it's going and how many samples do you require to get to within a certain amount of the true prices, quote unquote, we don't know yet. We are still in the process of analyzing it. Okay, so far what I have talked about is processing uncertain futures with data, but in the context of electricity market design, right? This is at the wholesale level. Let me now move to a long-term planning problem where, again, the conditional value at risk sensitive, but planning question, right? And this question is the following. At the distribution level, think about you have a collection of houses. Some have some solar panels on top of it with a certain capacity. So this capacity configuration of which house has solar panels and how much. That's a capacity configuration, call it psi. And then you think about a bunch of possible scenarios of load and solar irradiances, right? So those you call as the scenarios of solar irradiance and loads, capital omega, right? Then the question is, given this omega, what kind of size are okay for the network? What do I mean by okay? They impose essentially sort of acceptable risks of constraint violations or engineering constraint violations. So far, so good? Is the idea clear? So the question is, how much solar is too much? If I install too much capacity, can it disrupt certain engineering constraints of the network? That's all I'm asking for. Make sense? And so the idea is you have scenarios of solar irradiance and loads. You give me a capacity configuration that leads to a set of nodal power injections. You then sort of use a power flow model to get the voltages and the flows over the network. And that is some statistics. You process it through a risk measure. And again, whether it's acceptable or not, that's a matter of a modeling question, whether it's quote-unquote acceptable with the given scenarios that you have in mind, right? And again, we use conditional value at risk. You can pose this question and not getting into sort of the exact formulation here, but I mean, it is written here with some second-order cone programming relaxation of the network constraints and so on. I want to show you a sort of graphic to show what you can do and why we care about utilizing this particular kind of risk measure. So power system already has non-convexity. That comes from Kirchhoff's laws. You can't do anything about it, right? It's not a law you can repeal, as George Gross in our department says, right? So that already induces non-convexity. You can utilize convex relaxations, linearizations in the power flow model to deal with it. The reason I have chosen conditional value at risk to sort of work with is that at least the stochasticity does not introduce more non-convexity into the mix. And so one example of that use of convexity is the following. So think about what is the set of acceptable set of solar capacity configurations. That problem, if you look at it, it's actually convex after you do SOCP relaxation, conditional value at risk with scenarios and so on. So that set is convex. Now, typically what we are interested in is you give me a point and ask, is this acceptable or not? I have to run this giant optimization program, right? Even though it's an SOCP, it's pretty big. It takes around 40 to 50 minutes on a laptop to compute, okay? So I give you a solution whether it is acceptable or not. Now, typically, you're not interested in just one point. You give me a bunch of points. How do I do that? This is one place where we take advantage of convexity in a very specific manner. If I know that the set is convex, what can I do? Suppose if I know these 10 capacity configurations are convex, I know that its convex hull is automatically acceptable, right? And testing whether something is in the convex hull, that's less than a millisecond on a laptop. Make sense? If it is not acceptable, because of the nature of the convexity of the problem, I can create a feasibility cut. And I can even say, so if I find a point that is not acceptable, I can create a feasibility cut. And again, if something lies outside of that, I automatically know it is not acceptable. Make sense? So what is acceptable and what is not acceptable, I can create like a history by sampling more, right? And so this is a graphic that my student had done. This is mostly Avinash and Nate's work, where you sort of create these points and you sample more, and it sort of increasingly these inner approximations grow and the outer approximations shrink. And by 1,000 points, you've all basically characterized the region, right? And if you look at sort of the frequency of number of times I can use this like inner approximation or outer approximation to just guarantee it, it's most of the points. Out of 1,000 points I solved only 60 problems. And the rest of them, I could just certify whether they're acceptable or not using just memory that I built into the system. Make sense? This is sort of one of those examples where I'm doing a planning problem, where I'm utilizing scenarios. Data comes in as scenarios for me, but it's still a giant optimization problem. So I'm going to skip this and pose this particular research question that I think is fairly important. Power operators understand that the kind of sort of simplified formulations that we use, whether it's for planning, whether it's for capacity markets, these are very simplified. But think about the number of scenarios you may have to take into account. I was talking about this hosting capacity analysis. How much solar is too much? Well, did I account for the driving patterns that might be induced, which will change based on migration patterns? And migration has been changing city sizes over in the United States quite a bit, right? And there's ample data showing that. People's driving behavior would also change once you have EVs and so on. So you need even models to generate synthetic data of the future to be able to somehow do these planning problems, because our investments are durable. These are durable assets and are going to last probably 10, 20, 30 years. How do you account for the scenarios that has yet not happened? Historical data is not enough. And this is not a mere extrapolation using a classic, just fit a neural net and predict the future for this. It's not going to work because user behavior changes with adoption. How you drive changed as how the capabilities of the automobiles changed over time. And it's going to keep changing with electric vehicles and possibly partly autonomous, right? So the question is, if there are so large number of scenarios, is there whatever kind of risk measure, the one that is your favorite, choose one, and try to solve this giant stochastic optimization problem? We can't solve it. So going back to Srikant's question, can you do importance sampling or some sort of kind of a way to subsample and get representative scenarios such that, and ultimately you have to solve a deterministic optimization program whose solution is not too far off. The problem with solving that, and I want to look at this math question, but it's kind of difficult. Without solving anything, you can't a priori subsample. But if you solve a little bit, it gives you a little more information which samples are important and which are not, right? So some notion of adaptively increasing the sampling size, perhaps, is where the game is. And this is sort of, if we can solve this, is a clean optimization question. It will solve multiple questions on whether it's hosting capacity, expansion planning, capacity market design. We solve very simple deterministic optimization problems for capacity markets. Why? Because it's too large to solve for thinking about the number of scenarios one can think about for an entire year. Makes sense? So that's the goal, yes.
So this is kind of an
That was the hosting capacity analysis problem, yes. But this is more general. I'm just, yeah, these are offline problems, but these are giant optimization problems, right?
But you're
So
trying to find the samples that certify something.
that certify something. So I want some guarantees, right? I mean, if you say that I would process 10 years worth of data of demand supply scenarios to solve an optimization, a planning problem, right? A planning horizon of 10 years is huge if you think about the number of conditions that you have to account for. But that's impossible for any anybody to solve that, right? So how do you solve it with a smaller number of scenarios, but provide some meaningful robustness guarantees to your solution, right?
And these points you can pick, or you have to come from.
That's the beauty of it, right? So if you think about what operators used to do, back when the system was less complex, operators have this knowledge. What are the sort of pain points or the difficult scenarios? That's their wisdom, right? However, as the system becomes more complex and what part of the complexity from one part of the system interacts with which part of the stochasticity from another part, you don't know. And that becomes more and more complex to analyze. So you want to automate this process somehow. You can't rely purely on operator knowledge anymore. Make sense? All right. Okay. So that was sort of so if I were to sort of summarize what I've been talking about, the role of data here is to process uncertain futures, and my sort of work from our lab, we've been looking at, this is, most of this work was done by Avinash Madhavan, one of my students, Mariola Andrio, and my current postdoc, Nathan Dallin. So was basically on one part was on electricity market design, right? How do you process uncertain futures with data in actual market clearing? Then on long-term planning, which is hosting capacity analysis, asking how much solar is too much, right? Here, the role of the data is to process uncertain futures, right? The next part is sort of, the next two parts, it's going to be much shorter, and this is sort of part of ongoing work, some work that we have done, but some work that is fairly ongoing at the moment. So here, the role of the data is to learn user preferences, and what is that? So if you think about coordination of distributed energy resources, let's say I have a Nest thermostat that can be controlled in a smart way, or you may have an electric vehicle whose charging can be done within a certain deadline, or any kind of flexibility that DERs provide. How do you harness this flexibility? Now, you and I, our resources, however important they are to us, they look like a toaster to the grid. But when aggregated, the story is very different. So meaningful aggregations can then participate in the wholesale market, and that is what the premise of FERC Order 2222 is currently, right? To facilitate that. So now the question is, what kind of mechanisms, who will do what, and what kind of contracts will be written is now going to be anybody's sort of guess. And I don't think, given how wholesale markets have evolved in the United States, I don't think a single solution or a single architecture is going to be everywhere. It's not going to happen. I don't think so. There are multiple different paradigms people have thought about. It's a direct or price-based control by distribution utility, or it might be just a third party, which has nothing to do with the utility. These are third-party, profit-motivated retail aggregators who do this as a business, and they sell your aggregated quantities up to the wholesale market. Or you can even design a retail market at the retail level with automated bidding, right? So now the question is, I mean, we've looked at multiple different versions of this particular architecture, and we have some results, but I just want to share one example, okay, on retail market design. So this is mostly Mariola and a former student of Tamer Bashar, who also worked with me, Khalid Al-Shahri's work. And so the idea was to look at simple bid offer formats for a particular two-sided market. By two-sided market, I mean where there are demanders and suppliers, and both can be strategic. Okay? And so these are scalar parameterized mechanisms. By that I mean a supplier will only advertise or give you to the net market maker a single parameter that reflects a supply offer. Okay? Similarly, a demander gives you a single parameter. that reflects their demand bid. So these are scalar parameterized supply offers and demand bids. Okay, this kinds of supply offers has been investigated. Our inspiration was Ramesh Johari and John Tsitsiklis's work, but there were earlier works that also preceded, some from Tamer's group and Bruce's group from here, actually. So with these kinds of mechanisms, what my students sort of had proven, this is an IFAC paper, where if these demanders and suppliers are price takers, then it supports an efficient competitive equilibrium. But if they are price anticipating and suppliers are such that there is a pivotal supplier that exists, that is, the total capacity in the market is with one less supplier is not enough to cover the whole demand, the inelastic part of the demand, then Nash equilibrium may not exist. And without a pivotal supplier, a unique Nash equilibrium exists. And the solution is such that the welfare at Nash is not too different from the welfare, the social optimal welfare. This is not exactly welfare. There is a 3/4 and a 4/3. It's not the same ratio, but it's sort of basically the idea is that the welfare at Nash is not too different from the social optimal one. Now, this is all Nash characterization. Learning here? Okay, so with the same kind of supply offers, Mariola had investigated a particular different electricity market in the US and modeled it as a supply function competition. And that is what is called the coordinated transaction scheduling market. Let's not get into the details of that. But what I want to highlight is one result, that this is not a math result. This is just empirical. So the question that I had was, we had this electricity market in the US, these what are called the inter-area virtual bidding markets. We analyzed that using the supply function equilibria concept. Great. And we characterized the existence of Nash equilibria, properties of that Nash equilibria. What's the use of this? Because in a market setting, this complete information style assumption they're not valid. Bidders just repeatedly play in these markets and see what happens, right? Now, so what Mariola investigated was, let individual players play just a basic UCB-based policies, okay, and interact with this market. What ends up happening is, so think of this rather than thinking about exactly what price spread means here, et cetera. Think about this as the sort of extent of inefficiency in the market, okay? So where the Nash was actually efficient, these policies, notice that the outcomes sort of statistically match what we expect from it. But when the Nash is inefficient, statistically, even playing UCB-based policies, you're seeing each of these particular players have no idea what the market looks like. They just choose UCB-based policies. That's it, and UCB-based actions. And where the Nash is inefficient, notice that the outcomes from the UCB sort of reflect the efficiency difference between the two settings, which is sort of goes back to saying, this is not exactly convergence to equilibria, is it? But these simple policies reflect what we think the equilibrium characterization should reveal. And that's sort of something we are trying to understand. We've even investigated, this is one of my students, Arda, who's currently looking at it. Can simple policies learn equilibrium in a Bertrand game? And you have a very simple two-player game. And what we do is you have an affine demand with some parameters. You don't know the parameters. So this is parameter learning, but while pricing, trying to maximize your revenues. And this has a unique equilibria that can be characterized as a solution as a maximizer of a potential function. But just with Thompson sampling, it seems to converge somewhat, right? And the cumulative regret, is it optimal? We don't know. So we are trying to analyze. My goal is to understand two things in this particular aspect. One, can simple policies, where I don't know what the marketplace is, it's too big for me, I'm just a simple player at one house with an automated bidding strategy for my DER. And everyone's doing the same. Can I learn how to play in this market? And when I say learn, will this converge to equilibria? Even convergence to equilibria, even is it the right question even? Or something in a statistical sense like this is the right way to even analyze. So simple policies for single agent or single agent simple policies, how do they interact in a market? The answer, it will converge in a very wide class of games, is perhaps too much to expect. But what are the structures which guarantee something, whether it's in a statistical sense or convergent sense, asymptotically even, can we guarantee? This brings back to some of the work that Eric was presenting, and hopefully we get a better answer in the next few years in this direction. Okay, how much time do I have? A couple of minutes, okay. So now I'm just going to touch upon this work that we've been have started working on, and it's the following idea. This notion of transient stability analysis, completely taking our minds off optimization markets and so on. This is sort of going back to a classic question in power system. Okay, so I have a power system running fine. Something happens. A lightning strikes. Okay, a line goes down. A line goes down. A lot of current is flowing through it. So there is an on-fault trajectory. Right. Now, at some point, some circuit breaker will open and will isolate this fault, and you get post-fault dynamics. Right. Now, if you close this too late, what can happen is that the on-fault trajectory leaves the region of attraction of a stable equilibrium point of the on-fault of the post-fault trajectory. Make sense? So you need to arrest this in time. So far, so good. Something bad is happening, on-fault trajectory. My post-fault dynamics has some region of attraction. I want to do it quickly enough. I want to take that action to clear the fault quickly enough. That's the question of how long can I wait, is the question of transient stability analysis. Simple as that. Okay? Now, and people have looked at numerical integration, analytical energy functions. We've been looking at from simulation data. Can I get this region of attraction from simulation data? This is my student Boya's work with my collaborator Umesh. This is from this operator theoretic viewpoint, where the idea is, rather than analyzing the nonlinear dynamics of a power system, I want to lift this and look at it how either the density of states evolve or how functions or observables of the states evolve. And these are through these transfer operators called Koopman and Perron-Frobenius operator. Now, what are these? If you want to think about it, think about a Markov chain. The transition kernel is what pushes densities forward, right, or probabilities over states forward. That, in sort of more general state spaces, is your Perron-Frobenius operator. And its adjoint is the Koopman operator. Now, if these operators then work on function spaces, you have to choose a function space and then analyze their effects. The function spaces we choose are these reproducing kernel Hilbert spaces, RKHS, and these have lots of beautiful properties. Turns out that the Perron-Frobenius operator is a well-studied object called the conditional mean embedding operator. And its approximation with data, etc., have been very well studied already. So what we've been looking at is sparse learning of these kind of transfer operators and utilizing their spectrum to analyze ROA. So just to give you an example, this is a Duffing oscillator's two regions of attraction. And as you try to, this is basically one of the eigenfunctions of this operator that we learned over an RKHS. So what Boya's work does is she adds the kernels themselves. If points are too close, then you reject some samples, so that the data that you use to approximate these operators doesn't overwhelm you. That's the idea. Make sense? And so this sparsification, so this particular factor comes in because you're doing sample average approximation, was known. We add this extra factor because of the sparsification. So if you sparsify, you are going to get an even further larger bound on how well you can approximate this operator. So as you are increasing the sparsification, your spectrum or your eigenfunction is becoming less useful, right? Which is what you would expect. All right. So why are we using this? If I have a nice model for the power system, this is where the role of data comes in. We haven't done this part yet, and we are looking forward to it. Let's look at this. This is a NERC example that they gave. With inverter-based resources, if you take them and you model it with phasors, what we model the rest of the power system with, and you analyze stability, notice this beautiful blue line. You will certify this power system is stable. If you use more detailed EMT-based models, notice what you get. So the idea is all models are approximate. Are they useful? The question is, when there are incompatible models, one way to think about it is perhaps generate data from both and try to merge it in some meaningful way. That is possibly one use of data. And we are looking into how to be able to, these are two different time scales, and to how do we merge the data from these two in this operator theoretic framework is something that we are currently investigating. All right, so with that, I'll end the talk. So the three things that I wanted to just highlight and hopefully give you some problems to think about. The way at least I see it, the role of data is to process either uncertain futures, learn user preferences, or to tackle incompatible models. Thank you.
For the solar planning work, are there any policy in the solar work? Are there any policy implications for, like, should tax incentives be location dependent or anything like that?
It's a very good question. So currently, the solution or whatever we are investigating is completely just technological, right? And that too with very few constraints. We are only looking at engineering constraint violation. By that I meant only voltage violations and power flows on different line violations of those, right? There are lots of other considerations. But policy implications, yes, there are. But have we investigated them? No. That is, for example, just as you said, if I am going to give you a tax incentive for putting on a solar panel, should it be location dependent? If it is location dependent, does it make sense? Because what are the fairness aspects of that, right? These are things that go through stringent sort of public utility commissions weigh in on these and create these kinds of policies. Our prices, for example, retail price structure is not location dependent, right? We have either some tiered structure and so on, but those are, you and I, if we are in the same part of the grid, the distribution grid, we face the same, right? So fairness aspects also come into question, and I have not investigated those. Very good question. Thank you.